Alright, welcome back generals to another Let's Fix Generals 0 Hour to make the best game ever. Last video, we have continued efforts for the PDB reader in the unassemblize tool. And we got all the boilerplate code done for going through all the tree leaves symbols of DR2 API for function relevant symbol information. And now we would like to dump that into our own data structures. Right? Okay. So how do we do this? So the original, well, let's say the executable code that dumps it into a string list and then a symbol map and a section map. Yeah. Get symbol map. Yeah. Okay, we don't have to exactly use the same data structures. For starters, we can do our own. And then if things need to be unified, then we can like transform the data again. Maybe. Yeah. Okay. Let's open our dumped file here. Yeah. Okay, so I think what we need is a PDB function info, and then we need, what else do we need? Function info, certainly. We need a we also need a struct PDB source info. Yeah, it's like a source file information, like which function belongs in there and stuff like this. Source info. Yeah, so this would then contain a cd vector of PDB function infos. So std string file name, and then vector of pointers to this, maybe functions. Yeah, maybe. I do wonder, do we actually use DR source for anything? Yeah, we do. I see. Okay. What else is PDB doing? File. So basically we would have this file and then we would link to a function, and the function would have source info. How about we do association as an index? So we do vector win32 function indices. Yeah. So we have a vector of this. Yeah. Function. PDB source info. Then we would, we need to think about our data structures. Try to get it right. So we would certainly have a std vector of PDB function info, right? Functions. And then would also have m sources for this. And so this here would index this here. And it can grow, and the capacity can grow. It's fine. Function in this source info. Yeah. Then function info. Then we need a struct pdb source line info. Yeah, so here we need line number uint 32. I don't understand why this is auto completion. T. Then so let's go to our lines function. So it's line num. How about we use the same names as this one here? Line num. RVA. uint32 t RVA. Let's put a comment here. Relative virtual address. Line num. What is sec? Address offset. No, address section. Section. Well, how about we just give it full names then? Relative virtual address. Line num. uint32 t address section and address offset and then let's got this line number. I think that's it, no? Ah, length we need as well. Length. Okay. UN32T length. Yeah. So this should describe our source line info, and then in our function info we have put a std vector source line. We call this source lines. Then let's call this source file info. File. Let's call this just name. Source file info. Yeah. Okay, this makes sense already. So actually I do wonder, maybe we can make this part of source file info as well. I don't know. It depends whether or not multiple source files can have the same function. Is that possible? I don't know. That's a critical question. But we can't have two files with the same function, right? That would be duplicate symbol. I don't know. But then we need a very explicit strategy. If we put here, if we put the functions in here, that means we would first have to populate this vector. So the names. Yeah. Source file. I suspect the safer method here would be if we do a PDB compilant info, and then in there we put these things. So we have a compilant, which is this thing, and in there are our functions. There's a name. And then so this would be the compilant name. But we would like to, oh, man. We certainly prefer the source file over compilant, I think. Okay, let's fill the PDB function info first. We need to think about this more here. Ideally, we don't like touch our layouts again. So let's try to get it right. We have time, no rush, no rush, no rush. Okay, so our function would certainly contain the basically this stuff here. And Calling convention, yeah. Yeah, it's what is this here? Oof. Okay. Does this exist as a symbol? No. Let's call enums for this. Enum class function calling convention, and then take all these. Okay. So let's put this in here. Calling convention. Calling convention. And okay, so we have a bunch of different names here. We have undecorated names, name. Okay, let's search for this function name here. Okay, so globals. This exists twice here. Oof. Okay, so public symbol. Public symbol. Oops. Let's get name. So this is, how do we call this? Hold on. Mangled function name. Yeah, so this is a mangled name. Much more disgusting. Undecorated function name. So decorated name is this. Okay, then so we need a SCD string decorated name, aka mangled name. Then we will have a SCD undecorated name, and maybe we should also put like an example behind it. So like visualize it here. So SCD string, and then we had one more. This one here. This is global name. This here. Which is just this part here. Yeah, makes sense. This makes sense, yeah. But e.g. well, doesn't need explanation. Okay, what else do we need? Read public function, global function, that's just for the name. The function start and end. So we need this length here, I think. We still don't know what this length really means, right? So where do we get this? Here, length. Well, then the best we can do is call it length. Okay, let's put it here. uint32t length. And so we will have how about we put a struct PDB address, and in here we put this, and then we put this here, PDB address, and then we do the same here, address, and then we have another PDB address for for this here. Yeah, it's the same thing here. This here, which basically this matches this. Which probably is always the same. But it's okay, we can let's put debug start and debug end, right? Yeah, debug start, debug end. Now there is quite a bit of data overlap here. Like this number is always the same. This is always the same. I mean, this is definitely always the same. Yeah. I don't see this ever being different, right? So strictly speaking, there's always data overlap here. Like here we have 3 times this thing, the same value. We have an overlap here. Virtual address. But perhaps we don't care so much about the duplicates. Just for bytes, yeah. Yeah. Just Well, perhaps we don't do this. Perhaps what we do is so we put debug start well, it's always the same, right? What we can do is we can assert that this matches this. And if we ever get an outlier, then we can treat it. So we say so we simply put debug and relative address, and here debug and address offset. Debug and address section, same as debug and address section is identical to address section. Then we do here more comments. Hold on. Let's do a union. Unnamed union. How about that? Put here debug start relative virtual address. Then we have another union. Debug starts address section and debug ends. No, not debug ends. There, yeah, debug ends, yeah. And then we have union. We have debug here, this here, and debug starts address offset, and start ends, and then here we have another here. Yeah, this makes sense. It's very explicit. Yeah, and then we can put asserts to make sure that these really match. Yeah, then we don't need to have duplicate data. Yeah, it's not much, but when you have thousands of functions, this adds up, right? Okay, so we have relative virtual address, debug starts, and this, yeah. this and this. Yeah, I think this works. Yeah, this is good. Okay. Good. Then let's remove this. Okay. Do we want to have more information? So we have constructor. Constructor. Is constructor virtual base? Yeah. I think we don't care about all these different things. Yeah, I think calling convention is probably interesting to store, to have. Yeah, because it matters a lot for our function definition and declaration. But the other stuff here, I don't see it. Constructor, it's implicit with a name. Yeah. The other, I don't know if these are useful in any way. Yeah, okay, I think this is good enough for starters, yeah. Okay, so we have source line info, source lines. So this would then map this function to some source lines, which we don't necessarily need to fill much now, but we can. Yeah, okay. Good, yeah, this makes sense. And then our PDB compilant info. Yeah, so compilant info is very close to how the PDB has it organized. But the problem, we would probably prefer a stricter tie to the file, the source file. So I think with our build pipeline, they are the same. Compilant is always one source file. It's not strictly necessary always like so, depending on the build pipeline. But in our case, it likely is. With Visual Studio 6. Which is fine. We don't need to change that. But I do wonder, how do we want to make this association then? Source file info. Because we don't want to write the source file in here in the function. That doesn't make sense. How about we put this here, source file info, and we just have a name here. And we put a std vector with PDB source file info, source files, and then in our functions, we have a UN32T source file index. How about that? So that this would then refer to this index here. Source file ID. Perhaps we can also put the ID here. I don't know if it's useful for anything. ID name. Name. So I guess ID will be identical to index here. This is fine. Let's also call this ID. Let's make a comment synonymous to index. Yeah. Okay. Yeah, maybe we don't need this here. So we say, so we push these source files in here with the ID 0, 1, 2, 3, and so on. And then whenever we have a function, we set the ID here. Yeah. How about, let's look at our compactness here of the memory layout. Looks very compact. That's nice. Calling convention. Yeah. Okay. It's compact as well. Okay. Yeah. Okay, so our data structures, I think, are pretty okay. What we can also do is we can have here get UN32 get debug length, because we certainly perhaps, I don't know if that would be relevant, but basically, what is it? This minus this. So return here this minus this. Yeah, get debug length. Okay. Okay, I think this makes sense. Yeah, I think so. So I suspect that we will end up with one source file per compilant. And then the multiple functions. But strictly speaking, I think it's possible that a compilant could have multiple source files, but we will see. We will see. But I expect only ever one here in our case. But theoretically, it could be more. Okay, and then we take. Let's comment out these things here. So we will have a vector of these things. We call it compilants. It's maybe for index, synonymous for index. Okay, I think this makes sense. I hope so. It looks simple enough. Like all the info is easily laid out. We have a compilant. The compilant has multiple source files, multiple functions. Functions refer to the source file. The functions have a lot of address data in it. They have names. And they also refer to source lines. Yeah. I think this layout makes a lot of sense. We will see. Good, let's try to fill this vector here. It will be expensive to resize this thing, right? Because the compilant info. Yeah. We need to think about our sizes. I mean, we can reserve just like a big thing. Compilant. So we should build it once. I would say we create constructors for these, and there we reserve some sizes for the vectors, some reasonable sizes. And then we add a shrink to fit function on the compilant that calls into the others and starts shrinking things. And it's not much. We have these two vectors. This one. That's it. Okay, it's not much. Okay, let's so we will have a constructor And in here we say source files for dot reserve. So this one will be reserved with 1, and the other will be functions dot reserve. We reserve with what is our estimation? How many functions would we have per compilant? Let's start with 32. Yeah, it's was 16. I think 32 is okay. 16 or 32 somewhere. Okay, and then we add shrink to fit. Shrink to fit. Yeah. Void shrink to fit. And here we do okay, let's go over here first. Here we just have one source lines. By the way, this one shouldn't have M. So source lines. How many lines would a function have roughly? Let's go with, I don't know, 16. Yeah, let's go with 16. Source lines dot reserve 16. Okay. And then we put a void shrink to fit. And in here we do source lines shrink to fit. And what is wrong here? Uninitialized. Yeah, it's okay. We shrink to Can we get rid of this warning here? I know it's uninitialized, but we don't care. C++ ignore uninitialized Visual Studio. uninitialized variable constructor pragma warning ignore disable pragma warnings pragma warning okay, let's do this here. Let's see if it works. Disable. Okay, that works. Good. Then let's put this here and this down here. Okay. Then let's make a comment here. Missing value initialization. Okay, so shrink to fit. And so here we call for PDB function info functions or function we do function function dot shrink to fit, and then source files shrink to fit and functions shrink to fit. Basically, once we are done with a compilant, we call shrink to fit, and that will like compact our vectors to ideal size. And then yeah, the alternative would be to like loop over the data once to see how much is in there, then reserve the vectors and only then push. There would also be a possibility, but I don't think that's necessary. I think this is fine. It's not optimal because we eventually go through multiple resizes. I do wonder, is there a way to get this size? So here, read compilance. So this thing here. Oof. I wonder. I wonder what the better pick here is, virtual address or relative virtual address. This one is just 4 bytes large. But this one is 8 bytes large. To me, it sounds like that this is the real deal, the virtual address. But I'm not sure. Let's make a search for this. Relative virtual address versus virtual address versus relative virtual address. In an image file, the address of an item after it is loaded into memory with the base address of the image file subtracted from it. The RVA of an item almost always differs from its position within the file on disk. In an object file, an RVA is less meaningful because memory locations are not assigned. In this case, an RVA would be an address within a section to which a relocation is later applied during linking. For simplicity, a compiler should just set the first RVA in each section to 0. VA, same as RVA, except that the base address of the image file is not subtracted. The address is called VA because Windows creates a distinct VA space for each process, independent of physical memory. For almost all purposes, a VA should be considered just an address. A VA is not as predictable as an RVA because the loader might not load the image at its preferred location. Even after reading this, I still don't get it. Yeah. Okay, let's That's what we call the virtual address because they are visible only to each process and will be converted to different physical addresses by the OS. Visible only to each process. Physical memory address. You try to read address in a process, you get the content which is located on physical memory is what CPU sees. Virtual address is relative to physical address per process. RVA is relative to VA. File base or section base? File base. The value of RVA of a method is not always its offset from the beginning of the file. They are usually relative to some VA, which may be a default loading base address or section base VA. That's why I say you must check the PE format spec for detail. RVA 1000. Okay, but this explanation here doesn't match the observation. So to me, it looks like this is from the very beginning, and then here is section 1, which is 1000 hex less than this. So this one looks like the RVA to me, and this looks like the VA. But it's weird. That's a future address. Address section, address offset. Yeah, I don't know if virtual address is of any use for us. I mean, so far, relative virtual address looks pretty usable to me. So I assume that at this position in the executable will be the assembly code for this Unicode string. That's but we can double check it later. We'll see. Yeah. Okay. Let's keep on going. Yeah. It's so I wanted to know if we go to recompilance and we look at our enum children, this one, it has a get count. Uh-huh. But these symbols, they include all sorts of things. They are not just functions. Name search options. Find children. Okay. Yeah, I don't know. Okay, so I think here we do mcompilance.clear, that's the first. Then we do mcompilance.reserve capacity. P enum symbols get count. Long compilant count, or it just puts counts. Let's put a count 0. Reserve count. If it fails, then we reserve 0, but I suspect this will succeed. Yeah. And then here, so we will do a compilance dot mplaceback And then we will take pdb compilant info. I call it compilant info. Back, and then our compilant info. Compilant info. Module name. Compilant info dot name equals this name. I'm not sure if it's white char. Let's see. Oh, we cannot assign it. Okay. So we will have to so there has to be a W string. Yeah. Okay. Unless we say a city string. White string to string. Jesus. create util dot header. Let's put here util dot h. Let's compile. Reloads. Okay. Pragma once. SD string to string, or let's say to UTF-8 includes string includes, what's this? This. So the std w string str const converts str. Let's call this UTF-16. Return. Then we do another to UTF-16. std string UTF-8 to UTF. No, yeah. Here w string from bytes UTF-8 done. Okay. Let's put the header. If I'm not mistaken, we also used conversion somewhere else before. Here. Let's include util. And here, let's put a namespace util. And then w file name util to UTF-16 file name. This should work. Let's make this const. Okay, and then we also use it here. UTF from bytes 3 overloads. Is it also possible to do a CSTR here? Ah yeah, it's also possible like this. Okay, then how about we create another wchrt like this, and then the same here. Char. Okay, then we can pass this one, I guess, directly util to UTF-16, no, 8, and pass this. That works, yeah. Okay, great. Free string. Okay. I need water. Okay, we are back. Okay, let's put this also in here. I just realized. Actually, we can remove this here. Actually, we should probably it's okay. I drank the water a little bit too fast. Okay. In theory, it would also be possible to just use this BSTR there, but let's not do that. So. Okay. Okay. Okay, so our our children here unfortunately we won't be able to use the count of this for reserving because the symbols in the compilant are vast. But it's mostly functions, right? Sorry for the coughing, but I drank too fast and the water wanted to go into the lung. That's not good. Okay. So what I think we can do here is compilance dot shrink shrink to fit. So okay, let's do compilant info. Let's get another one of these here. How about I think we have to do this first, read compilants. Let's move this. Man, that's unacceptable. Okay, component info dot functions dot reserve count. What happened? What? Oh, gosh. Okay. Okay, so to me this implies that we don't actually reserve in constructors, but we actually well, let's keep this for now. Okay, let's keep on going. So very slow progress here, I have to say. Okay. Okay, so in our component symbol, we need to pass compilant info. And then in here, we need to oof. Yeah. Okay, then here we have to say compile and info dot functions dot emplace back. Yeah. And then compile ins dot functions dot back. And here we need to pass pdb function info here, function info, and the same here, and the same here, here, and here, and here. All right, and then here we pass this, and here's one. Yeah, this should work. Yeah, I think so. Because we definitely always go in here first, and then if it has children, it goes in here, and it just passes the last functions. Should work. Okay. Then let's go in here. Okay, so here we need to write stuff to our function info. By the way, I do realize now we also need to have a lookup for functions, but we get to that. We get to that. ULN. Okay, let's put this here. How about we simplify this? We just initialize this to FFF. Then 0, 0, 0. There's no need to make it complicated here. Okay, then we have call. DB call. Let's put a CV call unknown. 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 I can't write. Yeah. Okay, then let's assign this here. Let's do here dword. Then we have undecorated name. Undecorated. So it just shows the undecorated name. Then I wonder what will name be here. Okay, let's put a scope here. If get undecorated name, let's move this up here. So it's name, and in here we have this free string. Yeah. Let's, by the way, start assigning here function info dot address section is dwsec function info dot relative virtual address that, and function info dot address offset is that, function info dot length is ULN. So we downcast that. Static cast uint 32t. Well, I might as well just static cast all of these guys, but dword is 4 bytes, so not too worried about that, but we can do it anyway. Doesn't hurt. Function info dot calling convention static cast function calling convention call actually, looking at this, I do wonder if we should actually initialize the stuff here. Yeah, I think it makes actually sense. Let's remove this here. let's put here 0, 0, 0, 0, 0, 0, 0, and unknown. I do the same here. Better be safe than sorry. Doesn't make a huge difference in performance. Okay, we got undecorated name. So here we do function info dot decorated name equals. This is probably white string again, right? util to UTF-8 name. Yeah. I expected all our names will be ASCII at the end. So it's fine. So now it's interesting. What actually is get name here? Maybe get name will be global name. Could that be global name? Could be. Let's see. In that case, you wouldn't need to go through the globals. Maybe. Let's get name here. Function dot global name. Okay, do we have anything else? Free string. I think that's it. Yeah, let's delete this stuff here. Okay, yeah, this would be my suggestion for this function. Yeah. Basically just a bunch of getters. Assign this. Done. Yeah. Okay, this looks good to me. Then let's get to the next function, which is actually, let's see if it compiles already for starters. It should, unless I made a mistake, which is possible. No, I did not make a mistake. Very good. Good, then next will be the function start. So here we have a bunch of asserts. So I would say here we put yeah. Okay, I just realized, so this is called sect, and here we call it zeg. But zeg is not really, doesn't make much sense, right? Let's call it sec for section. Yeah, then we do the same here. My OCD commands me to use consistent names. Yes. Good. Okay, so get relative address. This. Okay. Maybe we should initialize these to 0. Or to xfff like here. Yeah. Sec and off. Okay. And then let's remove this. And so here we would say function info dot. Right. Right. Debug start. Aha, okay. So it's, what we simply do is we just put asserts here actually. That's it. Asserts. So this function does nothing other than asserting. Okay, well that's fair. So function info dot address offset equals this static cast uint32t. Yeah. Then the same for section sec, and the same for relative virtual address. There we go. Okay, and then we copy this stuff here, and then we copy this here, and this will be just a tiny bit different because we have this here. So debug int, which relative address, debug, and these two. Let's put a space here to make it easier to see. Offsets section offset RVA names lines. Okay, I think that's fair. So here we need to say function relative here if function debug int relative by the way. Sorry. So this is assigned to this, and debug and address offset function equals this. Okay, like that. Okay, so here we just assert this one. Yeah. Poor. Okay, let's compile this. Okay, let's put breakpoints here and see how this runs so far. Function info. So this should get us an address. Yeah, section, offset, get links, calling convention. Call near C. So we get undecorated name, static void, E12. And then this name will be just E12. So I think this name is actually our global name already. So I think what this means, we don't need to iterate through the globals later, which is good. Good. And then we got this function info. This has our data in here. And here, let's see. So this gives us 1000, yeah, which matches this one here. Section should be 1, yeah. And offset is 0 here. So this matches. No assert is hit. Okay, and here, similar story. This is different. This is the same. This is different. So it assigns this one, asserts this one. Yeah, perfect. Perfecto. Let's run this through and see if any assert is hit here. Aha. Assert is hit. Let's click on retry. Aha. Debug start address offset. Debug start. 4510. Okay, so this is different. Interesting. That is different. Huh. So after all, it can be different from the relative virtual address. Okay. That's interesting. Okay, it's unexpected, but it is what it is. Yeah. Now I don't know what this means. This debug start, debug end. Maybe we need it, maybe not. Okay, then what we do is let's create our struct pdb address, and we put this here, pdb address. So then we call this address debug start address debug end address. You know what? I think it can be different because it can be inlined. That's why. So you have a function. Yeah, of course. You have a function and it calls another function, but the function it calls is inlined in this caller function. And so the debug just continues like I don't know if that makes sense. But if it's inline, then it's also inline in the assembler. That doesn't make sense. Okay, forget what I said. I think I don't know why. I don't know what it means. Okay, let's comment out all this here. Okay, then let's call this relative virtual. And then let's call this, let's keep the full name. Okay, debug length is then debug end address dot relative and debug start address dot relative. Yeah. Okay, let's get back here. Good. So what we will do is we put here address dot this and this. It's a little bit much address here. Address. Well, I mean, looks like we should shorten this to section and this to offset. And then this one will be relative virtual. Yeah, let's do that. Okay, that's fair. Good. So we can't do a assert here. Then we have to assign it. So let's take this. Debug start address dot relative virtual. Debug start. Why is this not found? Oh, right. Okay, and then we have section sec, and we got offset. And then we remove this and that, and we take this. By the way, we can stop debugging. And then we copy this here, and here we put end address. There we go. Okay, then this should now run through. Yeah. Good. Let's oops, wrong button. Let's run this. This should be running through now. Yeah, it does. Relatively fast as well. Good. Then yeah, we have already a fair chunk done. That's good. Then let's remove this. remove this, and yeah, well, now we don't need those names anymore. Let's just like this. Okay. Good. It already looks very promising. Good. So globals, I suspect we don't need, because read globals. Yeah, let's skip that for now. But we will have publics. Publics. It's this one where we get this name here. Right? Public symbol, yeah. Okay. Okay, so we have this here. Here. Okay. So what we need is ooh. The way we have here separated function vectors for each compilant info makes it difficult to look up a specific function. Unless we had a pointer here. But we can't have a pointer because vector has unstable pointers to its elements. When it grows, it invalidates all pointers or iterators because it reallocates. So it would have a unique pointer if you want to have a unique pointer elements if you wanted to have stable addresses. Okay, how about we try to build the data flat? So we have compilants, we have functions, and source files, yeah. And then in here, instead of owning this stuff, we have vector, integer, source file IDs, function IDs. Yeah, let's comment this out here for now. Source file IDs. Let's comment this out as well. So this is synonymous for index. Well, plural indices. Yeah, so basically the compilant info will refer to an index in here. Yeah. Okay, this means here on read symbols, we then need to also put, hold on, should be M here, class member, whoops. Yeah, and we put here functions, source files, .clear, and functions, let's reserve it with something reasonable. So reserve, but no, it's fine, yeah. Go reserve how much? 1024, and then it doubles if it reaches that. And source files can have the same. Source files. Well, let's maybe put more reserve. 1024 times 8. I don't know, 8,000. Well, hold on. We have seen 200,000 functions, right? Let's go here with some. I don't know how many functions. 1600. Let's go here with like this. It's a lot of functions. And then here at the end we do compilants dot shrink to fit, which I think will do nothing because we will have a perfect reserve. But for these shrink to fit source files, shrink to fit. And here in functions, let's do for PDB function info for functions function dot source lines dot shrink to fit. I'm not sure if we need this. Let's comment this out for now. Read lines needs to be here. Okay, I think this makes sense. Good. Then we need to change the way the data is passed. Yeah, let's go in here. So here we have function IDs, right? Function IDs reserve count, yeah. And then what we do is we pass it here, yeah. And then we do functions and place back, and then we put compilant info dot function IDs dot pushback functions dot size static cast uint32t and then we place back, and then functions back goes in here. So basically our compilant refers to the function with the index. Yeah, that's fair. This should work. And then here we do the same. Pass this and that. Yeah. Okay, do we need to adjust anything else? No, I think that's it. Okay, so now the data is more flat. We still have some unflat data in here, but maybe that's okay. Yeah. Okay, but the flat data basically allows us now to create a lookup table for all functions. So we create SCD unordered map. By the way, don't we need to include vector? Include unordered map. So PDB address, yeah. So basically, unordered map key type is this PDB address, and then our map type is an index. I don't know if this needs a hood thing here. Maybe a relative virtual is enough. Let's go back here to our AVA based on section. Section offset. Relative virtual. Let's go with just this. Let's go with UN32T to UN32T. Yeah. So index to index map. Or let's call it RVA to function ID map. Yeah. RVA to function ID map. And what we do is here. So it reads the compilant function, and then we put here functions back dot address dot relative virtual equals function IDs dot back. I should do it. Yeah, so now we can look up the function ID, our function ID with a relative virtual address. And I suspect it will work properly. I'm not 100% sure, but let's hope. Hope is strong on this one. So the way I understand it is, so this is the RVA and this is the section virtual address, so to say. So this is a RVA from the beginning of the whole thing, and this is the RVA within the section. That's my understanding of this. I could be wrong, but maybe it's this way. And in that case, a relative virtual will be our go-to address for all sorts of users. Yeah. Okay. Then read compilant function, relative virtual. I think in the end we won't really need, we probably won't need this section offset thing, but let's keep it here for now. It doesn't hurt. Small data, I expect. Okay, so RVA to function ID map. How about let's put using address T equals this, and then we also using index T is also this. Then we put our index T, we put that here, and we put that here, and here, and address T we put here, and here, and here. Reason being, I think this helps a little bit with understanding, like, address maps to index, apart from the function name. Like, I think this makes it a little bit more clear, you know, just to help understanding. Because if everything is uint, yeah, then what is this? What is that? You know, this helps a little bit. Give the type a custom name, you know. Okay. Then yeah, I think that's good. Good. Then let's get to function ID map. Good. So our mapping is done, so this should be okay. Then what we can do next is we go to our... By the way, I think we can also delete this here. We don't need that anymore. This, yeah. Okay, so we need to read our publics. No. Yeah, publics, right? See? Yeah, here have the publics. Read public symbol. Public symbol. Okay, so what we will do here is we think we just need to have this RVA, and then we get this RVA here. By default, we make it FFF. Then we do here function ID map find RVA, and then that is, we need an alias for this. Let's do using address to index map T. Yeah. And then put that here. And then here we put address iterator. I think we can make a const iterator. Actually, no, it can't be const. Iterator it if it is not and then here name, name, get name, if name, then free string, name, and name free string and IT second, that's our index. Hold on. Second, so index T index, and then we do it. Let's do m functions dot index. So this gives us p function info equal this info. Actually, it can be considerator, right? This can also be const, and we have an error here. Function info, and then here function info dot, what is it? Decorated name. Decorated name is util dot to UTF-8 name. All right. Wait, this is wrong here. There we go. I think that's all we need to do, and then we can delete all the rest here. Yeah, this should do. Let's see if that works. What we can also do while we edit, let's go to read global symbol. Global here global function, and I think here, let's have a look here. Here, so I think here on the global function we can just make a test function info dot global name equals, no, we do assert equals this right. So basically here we just double check that the global name really matches this name here from this query. If it does, then it means we can remove this whole thing. Okay, let's see. No compile errors, perfect programming, of course. We never make mistakes, right? Okay, so for some reason this hits first. Why? Read global function, read public function. Okay, let's go to read symbols. Read publics first. Why did it not go in here? Let's put a breakpoint here. Okay, but this seems to work. Function info, global name, winmain equals winmain. Yeah. Okay, so far so good. Let's remove this here. So this is good, but I don't understand why the other breakpoint is not hit in public function. Huh? It's never hit. Why? It's not it now. It's public symbol. Let's look in our publics. Print public symbol. Aha. Must be a function or a data symbol. Okay. So public symbol here. Okay, so we put this here, public symbol. But the problem is like, but it's okay, yeah, because we look up. If it doesn't find it, yeah, that's fine. That's fine. Public read, public function. Yeah. Okay, let's try this. Let's remove this. Let's put a breakpoint here, just in case. Oops. Pressed the wrong button, but it was the correct button. Okay. So this public symbol goes in here. Yeah. And this one makes a lookup and it doesn't find anything because the symbol we can't see. Okay, then let's keep on trying and see if this hits. It does. Okay, so we got some hits here, and this one got the function create memory pool. Is this, let's check if this is also the first thing we see here. Here, public symbol. Let's go to the top. It should be a match. No, it's sabotage. Huh. What is this thing? So it's not a function, this thing here. Let's search for this. So we found this here, right? Create memory pool. Create memory pool. Name. Here, function info. Memory pool, this call creates memory pool. Int. Yeah. Yeah, it's this one here. Okay, but what is the first thing then? What is this? Wait, let's search for this here. Okay, it's not a function. It's not found, so it's something else. It's not a function, so okay, we don't care. Then that is fine. Okay, that's fair. Good, so we go to here, name, and then we should get this mangled name, yeah. And that's our decorated name. Nice. Name. Okay, great. Then let's put a breakpoint. Let's put a breakpoint on read symbols here. Put a breakpoint here. Here. There we go. And so we have 32 compile units. Okay. And we have capacity. By the way, let's restart this. It's really fast, by the way. It's very nice. Okay, capacity is 32 and we have 32 members. Okay, so this is perfect. Functions, we have 282 and we have reserved 100 to 1000. Okay, so this will shrink significantly. And then we have source files. Yeah, it's currently not filled. Yeah. Okay, this looks very good. Let's inspect our functions, see if these look good. This one has no undecorated name. Why not? Why does it not have a pass armor coefficients? It has no undecorated name. Why? They all have no undecorated. Huh? Okay, I think there's something wrong. What did we do wrong? Undecorated name. Ah. Okay, here's the error. Okay, well, simple enough. Okay, let's try again. All right, functions. Let's put that into our watch here. I think in the video it will be really small, but yeah, you have to put on your glasses. Okay, there we go. Very nice. Okay. Oof. Okay, let's take a screenshot of this. You can share it with the other developers to show the progress later. Okay, so this looks already really good. This works. Okay, then the last thing would be to create the files, the source files. Yeah, so hold on, let's debug this once more. We also forgot to push the source file IDs, I think. Wait. No, we pushed the function IDs. Okay, that's okay. Yeah. Okay, then the only thing missing now is here our source file IDs. Yeah. And source file IDs and source file IDs and calling convention. Okay, so we got this. We don't have this. We don't have this. Okay, let's clean up here a little bit. Source lines. Yeah, let's delete this. Let's delete this. Yeah. I even wonder if we need this function here. Maybe we don't. Okay, but this so far looks already pretty good to me. Do we have a to-do? Yeah, what to-dos do we have here? Read line, read lines. Okay, so just that. Yeah, what's the time? 3 hours 12. Yeah, I think it's a good time to end it here. And then tomorrow we can continue. Next video, we can continue with the line, the source file and the source lines assignment. And then the reading should be pretty much done. Yeah, and then we can carry on that data to the next steps. Yeah. Okay. How about we create a better screenshot? So we have compilers. Oof. Here. Compilers. And we have functions. Let's take a good function here. Oh, well, let's just create a extra image. Oh, what is that? Okay, right, looking in the name. Okay, let's take a screenshot of this here. Okay. Then I think we can remove read globals because it's not really used. So I would say we just add a comment here. Nothing relevant to get from here. Yeah, then we just remove this here. Okay, I think we can keep the boilerplate code. Like, doesn't really, don't need to remove it. Maybe we just compile this out if 0 and if currently not needed. Is currently not needed. Okay. Maybe we put the comments here. Okay, great. Yeah, we got the basics done for reading. So next video we will do, as I already said, we will fill the source file IDs here and populate this here in here, source files, and then also populate source lines here. Yeah, and then it should be done. Yeah. Okay, great. Then yeah, let's see if there's any interesting conversation on Discord regarding Thyme. If not, then we are not interested. No, we are not interested. Good. Then yeah, I wish you a great day or night. I hope you enjoyed. Until next time, goodbye.